Hokie dokie. Welcome to Math 1026, Lab 8. Today, we're knocking out the last lab of the semester. It's a good feeling, isn't it? Hope so. This is a long lab, so let's get into it. We're dealing with more super fun stuff, more cancer treatment-ish type stuff. Let's jump into this. Exponential models and corresponding linear models. So this basically goes into like fitting the correct model to correct data points. So like they have you put these points here on this graph, and they're basically like exploring the idea of, does a linear model, like a line of best fit these points, or does an exponential curve, a more curved function fit these points better, right? And so they're saying like add a linear graph, add an exponential graph, which model is better for the data? Well, if you were to draw like a rough line through here, it would be okay, but then if you fit an exponential curve, keyword curve, through these points, it would be a better fit naturally. So exponential would be the better model. Let's see. You need a better way to determine how well a model represents data by calculating something known as R squared. So it kind of deals with like correlation coefficients, which is R, and then R squared, yada yada. So for this lab, you'll be looking for R squared values that are close to 1, and that indicates that a model fits the data well. So in other words, if you have a scatter plot of a bunch of points and you fit a line of best fit, and you can calculate the R squared value of that line, if that R squared value is very close to 1, then that line is a very good fit for those points. But keep in mind, R squared values only make sense for linear models. So we'll be kind of playing around with the idea in this lab of converting exponential models or exponential curves, converting those into linear functions. And you did a little bit of that back in 1025, but it's been at least like 6 months. So I don't blame you if you don't remember that. So here they kind of demonstrate, if you're starting with an exponential curve, CE to the a times x, you can take the natural log of both sides, you can split up the natural logs, and then you get to this point where you have ln of y equals ax plus ln of c. And so they're comparing this to like mx plus b, right? Oh gosh, ax plus ln of c is mx plus b, so the m is the value in front of x, right? So that would be a, and then the plus b would be the plus ln of c, so b would be ln of c. All right, you can see those results upside down here. So then to see this result, blah, 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 Excel, find the values for, okay. So let's open a new Excel just to do this little thing they're asking of us. Where'd it go? There we go. So we'll do that, and we'll do this. All right, should have done this before, but that's all right. So ln of y. We're doing ty, ln of y. We're going to input the data that they gave us here in this little chart down here. 1, 1.8, 3.3, and 6. Okay, and the whole idea is if we just plotted these points, these t's and y's, that would give us that same graph we looked at a second ago. But what they want us to do is actually take the natural log of these values, because taking the natural log of points that appear to be on an exponential curve should translate those exponential curve points to a linear function. Should turn them into linear points, I suppose. So if you do ln of these y values, so ln of b2, and then drag this down, and then what we're going to do is highlight A and hold control. So hit A, hold control, click C. We'll highlight both those. We'll go to insert, scatter, move me out of the way. See how these are almost like more linear points now? So what we can do they ask us to do an equation. They just say plot the 4 points, draw the line through them. Oh, I think that was it. Okay, so it's demonstrating how it goes from an exponential curve to a more of a line situation. Okay, so I'm gonna leave it at that with that Excel situation. let's keep going with this. Earlier in this lab, blah, blah, blah. So you can go from exponential to linear, but you can also go from linear to exponential. So that's what they demonstrate here. They go backwards from ln of y equals mx plus b. They take the e, or make e the base of both sides, and then they split up the e, and then they split up the e some more, and then they rearrange it so it's like this. And so we have y equals e to the b times e to the m times x, and this is being compared to the exponential function y equals ce to the ax. So your c, your constant out in front of the e, is actually e to the b. E to the b is just some number, and so that's your constant c. So c equals e to the b. And then the a is referring to this coefficient in front of the x, right? And in this case, that would be just m. So m equals a, or I guess a equals m, and c equals e to the b. So, for example, suppose you have the linear model, ln of y equals 2x plus 3. So 2x plus 3, the slope is 2, and the b, so m is 2, and the b is 3. And we just see that here. It's not too crazy. So then, converting it to an exponential equation, the c would equal what? We said c was equal to e to the b. And so e to the b for this one would be e to the b value here, which was 3. So e to the 3 goes here. You can see that upside down here. They got about 20.1 for e to the 3. And then the a value, again, we said up here that a was equal to m, and m in this case was 2. And so a would equal 2. And so the equation would be what? It would be the c value, e to the a times x, so c e to the ax, with 20.1, or e to the 3, plugged in for c, and 2 plugged in for m. So you can see it upside down here, 20.1 e to the 2 times x. All right, that's all the time I'm going to spend on that. Let's go to the next one, tumor growth modeling. So in the paper that they give you, this whole like document situation, this whole journal article deal, they tell you to go to page 7 and look at the graphs. They say notice graph B is not simply an extension of graph A. Over the long run, graphs A and B represent two different groups of mice based on what? So let's get a little better look at what they're talking about here. So you go down to page 7, first one with the graphs. So we have these graphs. So just to roughly summarize, they have mice, and they're testing different like treatments on them. By treatments, it's more of like they're controlling their diet, and they're seeing how controlling their diet affects their the tumor's growth, that the tumor they might have's growth, I guess. So there's graphs A and B, and they were saying on the surface they look very similar, right? There's tumor volume, there's days of therapy, tumor volume, days of therapy, and they're saying graph B is not just an extension, it's not just more days, but it's actually measuring different data, I guess. It's not just the extension of it, because if it were an extension, this green line would be way up here over here, but it's not. The green line's way closer to the blue line for the graph B, and so on. So the difference is the method they're using. Let me be more specific. It's like the calorie, what they call it, the cell line. That's what it was. So the cell line is the difference. So they're using the cell line SHSY5Y for graph A, and then SK and BE2 for graph B. I think they say it again here. Their injection, it's an injection of 2 neuroblastoma cell lines. So like one graph is representing one cell line, the other graph another cell line. And then they ask like which one's which, I think. Which cell line is represented in each of the following graphs. That's what I just went over. SH is in graph A and SK is graph B. For number 2, we got 4 plots for each graph, SD, CRSD, KD, and CRKD. What do these abbreviations mean? And so SD, so let's find page 4 like they were talking about. I think it's right here. So 4 different regimens. So SD is your standard diet. CRSD is your calorie-restricted standard diet. KD is your ketogenic diet. and CRKD is the calorie-restricted ketogenic diet. So that's pretty much it for all those. In the context, which diet represents the control group? Well, if you look at these four, I would say the most like the one regimen that's like the what am I trying to say? The one that represents more of a control group than the others would be the standard diet, because it's the one with like the least amount of restrictions. The word standard feels like it gives it away, right? It's not calorie restricted. It's not ketogenic. That's pretty much it. That's how I would decide that. Okay. Number 4, what do the values on the coordinate axes of A and B represent? We kind of looked at that already. Again, the axes, the x-axis is days of therapy. The y-axis is the tumor volume in millimeters cubed, so cubic millimeters for both graphs, right? In graph B, one of the 3 treatments does not appear to be successful. Which one? So in graph B, keep in mind they say one of 3 treatments. So I think the idea is like once we've identified the control group as the standard diet, there's 3 other actual treatments apart from the control group, right? So they're saying one of those 3 treatments does not appear to be successful on graph B. So looking at graph B here, keep in mind the green is the standard diet. So that's like our control. So we're not considering that as one of the 3. So of the remaining 3, which one doesn't appear to be successful? Now, to be successful, well, think about what it means to be successful. Well, the tumor volume is what they're measuring. And what they're trying to do is shrink the tumor volume, right? Or I guess like slow its growth or something along those lines. You don't want the tumor to keep growing and growing and growing as it does for the standard diet, right? So it appears the one color that's kind of going along with the green line, that standard diet, would be the blue, so the ketogenic diet, because the other 2 colors are really helping the tumor growth stay kind of at bay. It's keeping it from growing too crazy, but the blue line, the ketogenic diet, looks like it's just growing right along with the standard diet. So that one appears to be not successful. Yeah, all right. Now that we have a better understanding, it's time to create a mathematical model for it. You're just going to focus on the data in graph B. We're opening Lab 8 data set, and let's do some linear models. Yeah, I think I can talk us through this. We'll go back and answer these questions before we move on to exponential. Okay, let's get into it. So get rid of that Excel document, don't need that. So opening this up, we're doing our 3 linear models. So these 3 tabs down here, starting with SD. So all we do, we can just highlight A and B, insert, scatter plot, boom. Click on this open space here on the graph. Go to add chart element, trend line, more options. Linear should already be selected because we're just creating lines of best fit. We're going to display the equation, and we're going to display the r² value. So we'll drag those over there. We can exit out of that. I think that's all we need. These are our equations that you would hypothetically plug in to this chart here. So this is your SD. This is your standard diet. Yeah. Okay, sorry, I'm just confused why they didn't give us the ketogenic diet. Made me wonder if the ketogenic might have been the control group. Nah, I'm not feeling that. Okay, we'll just roll the flow here. So SD, this is SD. This first equation is your linear equation model. And then r² is 0.92. Okay, that's pretty good. 0.9242. They say round everything to 2 decimal places. The equation should be good, but r² would just be 0.92. So let's keep it going a little bit faster here. Linear model, highlight A and B, insert, scatter, boom. Go over to add chart element, trend line, more trend line options, go to linear, display equation, display r². Drag that up, we'll zoom in a little bit. This is our equation for CRSD. This is our r². R² would be about 0.87 if you rounded. And also, I guess, make sure to round those to 2 decimal places. All right, let's do this one. Highlight A and B, insert, scatter, boom. What am I doing? Click on the graph, add chart element, trend line, more options, display equation, display R squared. We have our equation, and then our R squared. R squared is about 0.85 for this one. Okay, so now with those 3 equations and R squared values, they say based only on the R squared values, which of the linear models fits its data set best. So we're looking for the R squared value, remember, that is closest to 1. So this one's 0.85, this one is 0.87, and this one is 0.92. So 0.92 is the closest to 1. So SD, the standard diet, would be the linear model that best fits the data set. Assume for the sake of the argument that all the data sets do follow a linear model. What would this say about how the tumor grows? So I think the idea is like assuming they all follow a linear model. I think they're saying like, trying to wrap my head around, because they say think about the rate of change of a linear function. So rate of change of a linear function is constant. It's growing at the same rate. So I think that's what they're saying. Like assuming the linear model best fits it, what would you say about how the tumor grows? It grows at a constant rate, I guess. I was also on the fence about saying like the standard diet, if a linear best fits the standard diet. I don't know. I think it's just something along the lines of it grows at a constant rate. I think that's the idea. Okay, exponential models. So I think it's the same idea. We're just doing exponential models. So click graph B. What are they doing? Okay, yeah. So let's go back to graph B. They say looking at CRSD and CRKD, which one appears to fit an exponential model better? So which ones? Both the CRs, so both the calorie restricted, the pink and the orange. So looking down here, the pink and the orange, which one fits an exponential curve a little bit better? So naturally, I'd probably go with orange because it kind of has that curve up. It like ramps up a little bit better than the purple does, because purple kind of ramps up, but then it kind of flips like the opposite way. So I'm going to go with CRKD, calorie restricted keto diet. Remember, R squared are only valid for linear functions. We're going to go to the ln tab for each of them. We're going to find the ln values, and then we'll create linear models for A and C, columns A and C, display the equation, yada yada. Okay, let's do it. So looking at the first ln of SD, so we need to find ln of SD by doing equals ln of this, close that off, drag that baby down, and then we're going to do the same thing now but with A and C. So click on A, hold control, click on C, go to a scatter plot, boom, these lines or these points look a little more linear. Add a trend line, more options. Make sure you click on this bar graph if it's not already there. We're still doing a linear function. I know it's an exponential curve section, but the idea is we're treating these points as exponential and we're converting them to linear by using the natural log. Okay? Okay. Display equation, display R squared. Boom. Look at that. Okay, so we have our equation. I think they have you plug it in here. Yeah, so equation for natural log of y. That's the idea of like turning it into a linear function, right? So you'd plug in this function right here. So 0.09, if you're rounding to 2 decimal places, right? 2 decimal places. So 0.09x plus 5.11 for the function. And then R squared is just 0.99, so very, very high, very close to 1. And then we'll talk about the equation for exponential model once we do all 3 of these. So let's keep going. All right, I'm doing the same thing. ln of CRSD. do ln of this. Oops. Drag that baby down. Click on A, hold control, click on C. Insert that. We have a much better looking linear appearance. Display equation, display r squared. We're doing all the same stuff. Hopefully I don't need to keep saying what to do. Our equation is 0.07x plus 4.84, and then r squared is about 0.97 if we round up. Okay, also much better than the other linear one we did. So ln of CRKD. So this one we're doing ln of this value. We get this, drag this down. A, C, insert, scatter, chart element, trend line, more options, bam. Display equation, display r squared. Our equation will be 0.05x plus 0.491, and then r squared is 0.94. All right, so now you should have these first two columns, plugged in, or you know exactly what goes in those columns now. So now the equation for the exponential model here is where we're kind of doing what we did on the very first page of the lab and converting something that's in the form of ln of y equals back into the equation for the exponential model. So I'm going to try to do this the best I can using what we have here. So ln of SD is where I'll start. We're going to convert this equation that looks like this back into an exponential model using a little guide here. We're going to use this, and I didn't write it out, so it's a little tricky, but we're going to use this as like the starting point, right? Because 2x plus 3, that's like mx plus b, that's what we're starting with, and we're converting it into this equation that is upside down. And this equation comes from e to the 3, or e to the b value. In this case, it'd be e to the 5.11 as the the coefficient out front, and then the slope value, the 2 that we can see over here in the exponent, comes from just the slope value here. So let me just type it out. It'll be easier as we go through it. So to convert this to an exponential curve, we are doing e raised to this b value. So it's literally I'll just like type, yeah, I'm gonna type it like this. So like e raised to the power of 5.11, and then that is multiplied by the actual e raised to the power of 0.08. I might round that up actually. I don't think I did that the first time. So 0.09 x. This is our exponential function. So like this coefficient, let me see if I can do one. I'll draw one more comparison to this. So we were writing the linear function, the mx plus b, as an exponential function, c e to the a times x. So e to the 5.11 is our c. E is just this e, and then a times x is 0.09 times x, and that 0.09 comes from this slope right here, and then 5.11 comes from that value there. So what I've typed out here is the equation for the exponential model for SD. All right, let's keep going with the others. So this one would be e to the power of, I'll do e to the power of 4.84, and then that would be times e to the power of 0.07x. And that's it. That's your exponential function. All right. And then let's do this last one. Just type it right here again. Y equals e to the 4.91, coming from the b value, I'm getting them right here, right? 4.91 times e to the 0.05x. Make sure that's in parentheses if it's not clear already. All right, so I'm just typing these here as if I'm filling out this table here. Obviously, this is not going to calculate something decent in Excel. I'm just writing them out somewhere so you could, if you wanted to, translate them to the, or transfer them to the chart here. Okay, let's see what's next. In order to complete the last column, convert, blah, 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 round to 2 decimals. Do you think the exponential models fit the data better than the linear models? All right, so how do we know if they fit them better? Well, we're looking at the r-squared value again. So the r-squared value, 0.99, 0.96, 0.94. All those r-squared values are higher than the linear model r-squared values, 0.92, 0.87, 0.85, right? So the r-squared values being not just higher but closer to 1 would mean that the exponential models fit the data better than the linear models. So describe how the r-squared values and the graphs actually support your answer. We already described the r-squared values, but the graphs, I was saying it as we went along, but see how, like, once you converted them, so like before we converted them, you can see they have like more of an exponential curve to them, but then we translated them to linear functions and they all kind of fit a linear image better. So that's the idea. Assume for the sake of the argument that all of the data sets do follow exponential models. What would this say about how the tumor grows? Okay, well, I guess they would grow exponentially. So the rate of change for an exponential function, it starts off very slow, I guess, like, and then eventually it like picks up and the rate of change gets faster and faster and faster and starts growing out of control. Yeah, and so I think the idea is that I think because the exponential model fits all of them better, that typically tumors do grow exponentially, and that's why you'd want to stop them before they start growing out of control, because once they start growing out of control, it's game over. Compare all the information you have for CRSD and CRKD, including the graph. Which data set appears to follow the exponential model more closely? So now comparing CRSD, CRKD, CRSD, CRKD. Okay, well, follow the exponential model. So I would just look at these two, ln of CRSD and CRKD, and just pick the one with the higher r-squared value, I think. So that's 9.4, this one's 9.6, 9.7. So I would say ln, or I would say CRSD appears to follow the exponential model more closely, because once you converted it to a linear model and took the, or find the r-squared value, it matches it better. Suggest a different model for the other data set that might be a better fit. Okay, well, linear is still pretty good for KD, but shoot, I don't know. I mean, I still think exponential is still a good fit for it, but I'm curious if we went back to like this stuff here. So we said, well, that's interesting actually. Did we see SD? Yeah, we said CRSD was the better fit exponentially. That's kind of funny, because I think originally we said the orange one was better exponentially, right? But it appeared that the purple one was better exponentially. It's like these two bumps right here kind of threw off what we thought initially. Another model, they say use another model. They say suggest a different model for the other data set that might be a better fit, or call all the model. I don't know what all models you would have used besides linear and exponential. Shoot. Yeah, I don't know. I'm not going to spend too much energy on this. I would say exponential is still probably pretty solid. Let's not waste any more time. We're almost done here. Application of tumor model. How are we doing on time? 29 minutes. I thought it was going to go like an hour. We'll see. Still time left. Now that you've calculated different models, let's see how we can use them. You'll need to define formulas in Excel. Okay. So a tumor volume of 3,500 probably meant death, or meant probable death for mice. Now for a human, it's probably higher, so they're using 10,000. So determine approximately how many days it would take for the SD tumor to reach 10,000 using both your linear and your exponential model you developed in the previous section. And I think we're going to do this for all of the models. So for the SD models only, you're given values to check. Okay. Rounded to 2 decimal places. You got to check those. Okay. Let's see if I can make sense of this. So let's start with the SD linear. Oh, I don't like that. Hold up. There we go. I'm just going to use, we're going to do SD linear, and then we'll do SD exponential. So SD linear is this one, and we're going to plug in, I guess, 5 just to check that 125 is the correct value. Okay. So rounded to 2 decimals each time, we're doing 78.46 times x, which we're using 5, and then minus 266.62, and we get 125.68. That checks out. And then for the exponential model, we're hoping for 259.82. So we go to the exponential model, which we typed out here. Again, pretty rough, but let's type in the real deal here with 5 plugged in. All right, here we go. Oh, we're doing EXP of 511. All right, something's messed up. Hold up. All right, EXP of 511 times, oh goodness, now I can't see it. EXP of 511 times EXP of 0.09 times x. So 0.09 times x, which is 5. So here's the equation all together up here. This is me plugging it into the exponential version. 259.82. Hey, that matches up. Okay, so that's a safe bet. So now, that's just like to help us check our process, I guess. But we're trying to find how many days. We're trying to solve for x, I believe. X is time, should be. How many days it would take to reach 10,000 using both models. Okay. So let's start with the linear model. That'll be easier. And so what we're doing is setting 10 equal to y and solving for x, given this equation here, right? So, or sorry, what did I say? 10? 10,000 is what I meant to say. All right, we're setting 10,000 equal to y and solving for x. All right, so imagine there's a 10,000 in here, right? We're solving for x, so we're going to add 266, and we're going to divide by 78 point yada yada. I'm going to put y back in its place, but then I'll type it all here. So we're doing 10,000 minus, or sorry, plus 266.62, because we're adding the 266 from here to the left side. We're going to close all this off, and we're dividing this by 78.46. All right, we get 130. This is the amount of days it would take for 10,000. This is linear. I'll do like exponential here. Okay. So I'm going to go ahead and do the exponential. Oh gosh, do I want to do that? I'm just going to do all the linears first. I'm going to do all the linears, okay? I'm going to just copy them so we get kind of like a base situation here. So we did the linear for the first one, right? Let's do linear for the second one, CRSD, so we can just change these little bit of values, right? So we're going to add, for this one, we're just going to change 266 to 88.97. And we're going to change the 78.46 to 38.8. All right, so that's going to take 260 days. Let's go ahead and do it for this one. Again, we're changing 266 to the y-intercept. In this case, it was plus, so we have to change it to a minus. So notice in the last two, the y-intercept was negative, or it was subtracted, the b-value subtracted, and so we have to, holy cannoli, I just messed up all that stuff. All right, hopefully it didn't change. Oh my god. All right, just gotta back this up, sorry. So annoying. We're subtracting 35.467, and we're dividing by 20.69. All right. Good night. All right, I'm gonna use 2 decimal places here. I almost forgot. Okay, enter. It's gonna take 481 days. That's pretty good. All right, so now let's do, so what we just found, all the linear values, all those linear values is the days it would take for the tumor to reach 10,000 millimeters cubic millimeters. So that was for SD, that was for CRSD, and that was for CRKD. We did all the linears. Now let's do all the exponentials so we can keep it consistent. Now all the exponentials, where are we at? We're at right here. Right here, we're using, using this stuff. Okay. Now, I'm wondering if we could just use, I guess we gotta use this. I'm curious if we could just use this equation here. I feel like we can. Oh god, let me try something real quick. I don't know if that would be right, because if I did 5 in there, you'd have to take like ln. Yeah, it wouldn't quite be the same, because this is like ln of y. That's annoying. Okay, so we're still plugging in 10,000 in place of this y here, right? So plugging 10,000 in there and solving for x. Okay, I think we can do that. What we're gonna have to do is divide by e to the 5.11, take the natural log of that, and then divide by 0.09. All right. Should have got my iPad out for this, but just bear with me. Taking the natural log, 10,000, divided by e to the 511. So exp 5.11. Bam. That's our first part. We've divided by the e term, and then we've taken the natural log of both sides to get e by itself, or sorry, e to get rid of e, to get 0.09x by itself. Then we divide by 0.09 to get x by itself. All right, that was ln. We should just be able to close that off and divide by 0.09. Okay? Okay? All right. It's going to take 45 days. So, praying that I did that right. This is for the exponential. It's going to take 45 days, which is bonkers, because we said 130 for the other. Okay, let's keep going. We're going to copy the same equation. It's going to take that many days. We're going to do the same format for the others. All right, so let's give it a go. ln of 10,000, exp of, in this case, 4.84. And we're dividing by 0.07. Hit enter. 62 days. Go ahead and change this last one here. exp of 491. And then dividing by 0.05. Hit enter. We get about 86 days. Okay. So what do we notice? The exponential gives us far less time in terms of the number of days it'll take to reach 10,000 cubic milliliters. Okay. The reason is probably because the exponential models like fit the data better, and so yeah, it's probably more accurate, I guess is what I'm getting at. So even though it's less days, it's probably more accurate. So anyway, what we just found were the number of days it'll take to reach 10,000 cubic millimeters. So it was 45 days, 62 days, 86 days. Okay. When you're looking at the real data, it's important to be smart about using R-squared values to determine which model is the best fit. It's often more important to look at the bigger picture of what you're trying to model and how you expect it to behave than to simply say this R-squared value is higher than that one, so the first model is better, which I did a lot of this lab. So based on what you've seen in this lab and your general knowledge of cancer, which of these models do you think best fits the data? Why? What are the risks if you use the wrong model? Now, wow. Okay. So, I mean, I'm going to first go off of, since this is an extension of, you know, the number of days it takes to hit 10,000, I'll probably start there. So for each of these models, 45, 62, CRKD, 481, 260. CRKD is in the lead in terms of how many days it'll take to, you know, hit that max point. Also, looking at this data, CRKD is still like it's holding off the growth of the tumor, right? It's slowing the growth of the tumor visually more than any of the others. What else we got? What else they ask? How you expect it to behave? Which of these models do you think best? But they're just asking which one best fits the data. Huh. So are they just, hold up. Are they just asking about, am I answering the wrong question? Hold up. No, it's definitely exponential. Okay, I think they're just asking like linear versus exponential. That's stupid. Okay. They're not even asking like which treatment. Oh, okay. Well, in that case, I would just say exponential best fits the data. Why? Because not only the R-squared values are higher for each one, you can just see the points that they just look more exponential. I don't know. The risks are, if you use the wrong model, you're getting a difference of thinking you're going to survive 130 days when in reality you only have 45 days. Or when you think you're going to survive 260 days, you only got 60 days. So that's the, okay. So it's still kind of related to what I was talking about with each of the things, but those are the risks. So exponential better fits the data for a number of reasons. We've seen the R-squared values, the visual representations, I don't know, it just fits the data better. It looks more exponential. And the risks are you can really mess up someone's expectation of how big their tumor's going to grow at what day. You know, it's going to mess up their whole timeline. All right. That's about the best I got here. Hope you learned something. Hope this helped. I know it was a little tricky at the end there with calculating these things. So I apologize in advance for that. All right. Well, hey, you knocked out the last lab. Just got to take that quiz. If you have any questions on the lab, you let me know. Thanks for working out these labs with me this semester. It's been a fun time. Hope everyone never has to deal with these labs ever again in their life. I think that's about it. How long we go today? About 44 minutes. It's about what I expected. All right, it's pretty fair. All right, if anyone has questions, let me know. I got nothing. My brain is mush right now. So I'll see you. Have a good one. Bye-bye.